Hello to you watching this video. So in today's video, we would now be solving for this problem for pre-stressed concrete using elastic analysis. So in this problem, a simply supported symmetrical I-beam shown will be used on a 15-meter simple span beam. It is to carry a superimposed dead load plus live load of 13.6 kilonewton per meter. So the beam will be pre-tensioned with multiple 7-wire strands with centroid at a constant eccentricity of 220 millimeters. The initial pre-stress force immediately after transfer will be 800 kilonewtons. So this is now our pre-stressing force immediately after transfer. Okay, so the specified strength of the concrete is 35 megapascal. So according to the design, it would be 35 megapascal. But at the time of pre-stressing, the strength was 27.6. So if you're wondering why is it different? So again, this is the initial and this is the final. So maybe during this time or during the immediate or let's say that during the intermediate stage, it has cured and it has increased its strength into 35 megapascal. So we will also assume a time-dependent pre-stress loss of 15%. So in this problem, it is stated that the pre-stressing tendon would now be having a constant eccentricity of 220 mm. So what is the eccentricity? When we say eccentricity, that is the distance from the neutral axis up until the pre-stressing tendons. So with that, guys, it is now measured once again from the neutral axis up until here, the center of the pre-stressing tendons. And according to the problem, that is now 220 millimeters. Okay. Also in the problem, once again, it is stated that it is under constant eccentricity, meaning that our figure will now look like this. Okay. Okay, so we will now be calculating the following. So first, we will be calculating the stresses at the supports during the initial stage. Then after that, we will now be solving for the stresses at the midspan during the final stage. Then we will now be solving for the allowable stresses according to NSCP for uncracked provision. Then let us now check for the adequacy of the beam. Okay, so what is now our approach here? So first up, let us solve for the stresses. And how can we solve for the stresses of this section? So suppose that this is now our pre-stressed beam, whereas we have our beam, we have our load, and then we also have our force here. So this is now our pre-stressing force. So I don't know to you, but if it would be up to me, I would rather separate the analysis of the beam action and the pre-stressing action. So with that, guys, once again, I would rather separate the both of this. Okay, so since they are separated, I will now focus first on this beam to the left. So if this is now the beam to the left, the tendency of this beam is now to bend in this particular manner. So if it would bend in this manner, I could also say that the fibers here at the top part would be under compression and the stress at the lower part will now be under tension. So let me write it here. So this is now under compression and this is now under tension. So for my example, or in this video, my sign convention is positive for tension, then negative for compression. Okay, so this is now my sign convention for this video. So feel free to change your sign convention if you want to. But once again, in this video, this is now my sign conventions. So proceeding, guys, if I am now to draw the stress diagram, once again, the top portion would be under compression and the lower portion would be in tension. So this is now the stress diagram. So since compression would be negative, I will be plotting it to the left. So this is now for compression. And for tension, since it is positive, I will be plotting it to the right. Okay, so that is now for the beam action. So let us now proceed to the pre-stressing force. Since we have here an eccentricity, so once again, the tendency of this beam is to bend in the opposite direction. And with that, if you would now be looking at our new figure, The fibers at the top will now be in terms of tension, and the fibers at the bottom part will now be under compression. So, drawing our stress diagram, it will now be the other way around. Whereas the top part will now be in tension and the bottom part will now be under compression. Okay, but the thing is here, we are not yet done. Because aside from this figure or this beam being bent in this manner, it is also subject to an axial force. As you can see that this force here is parallel to the cross-sectional area of this beam. We could say that this particular beam is under compressive stress. So with that, guys, this is now due to compression. Okay? So again, with that, guys, if we are now to proceed to the next slide here, this red diagram here, so this red diagram here is the stress due to the load. And this one at the middle, this is now the stress diagram due to the moment caused by the eccentricity. So this bending here. And for this diagram is the stress diagram due to the direct axial pressure due to our pre-stressing force P. Okay? So let me just go back to the middle diagram here. So how can we solve for this, or why did it bend upwards in the first place? So let me just hide everything and let us focus on this particular slide or this particular figure. So again, when we say eccentricity, it now is the distance from the neutral axis up until the pre-stressing force. So let's suppose that this is now the neutral axis. And if we would be measuring this value, this is now the eccentricity. And if this is P, okay, if that is now P, since we have an eccentricity, if we would now be multiplying the force by the eccentricity, this would now produce a particular moment. And from that moment, this is now that moment. So this is now the moment. And as you can see, that this moment, or the effect of this particular moment to the beam, is that it would bend it upward. So thus, in our previous slide, where was that? So in our previous slide here, this here is under tension and this is under compression. And once again, if you would be looking at this diagram, this is the stress diagram due to moment caused by eccentricity. Okay? Proceeding. Okay, so let me just go to the next slide. So let us go back to these diagrams. Okay, so next problem. Now that we know the diagrams, what do we do now? So how can we solve for the stress in the first place? So since this is more important than the figure at the top itself, so let me hide the figure at the top and let me move that upward. And from that, guys, once again, how do we solve? So if you can remember from your mechanics of deformable bodies, or let's say the strength of materials, for elastic materials, the bending stress is equal to mc all over I. So that is now the bending stress, where c is the distance from the neutral axis up until the fiber that you are analyzing. Okay, so proceeding, let me now first plot this line here, and let us assume that that is the neutral axis. So if that is the neutral axis, I will now be writing YT and YB, and from that, let us assume that YT is the distance from the neutral axis up until the furthest top fiber. And for YB, let us assume that it is the distance from the neutral axis to the extreme bottom fiber. Okay, so with that being said, since this first one here is the stress diagram due to the load, so from that, the equation here at the top is still mc all over I, but our m is, of course, the moment. C is the distance from the neutral axis up until the fiber that we're considering, which is YT, divided by I. or Ix in this case, since we are to get the moment of inertia about the x-axis, because our figure is actually upright like this. So if this is the neutral axis and the manner of bending would now be in this direction or in this direction here. So meaning that we will be solving for Ix, okay? So proceeding, where is that slide again? So not this one, rather this one here. So what is now the formula for this portion? So once again, that is MC over I, or the FB at the top is M, but C is equal to YT divided by I. So proceeding, what about for this bottom one? That is M times YB over IX. So next up, what about for this one here? So what is now our formula for this particular diagram? Because if we would be looking at this slide here, if we are to look at this slide, it did not have any moment. But once again, it did actually. And the moment here is actually equal to P times E. Okay? So once again, the moment is equal to force times eccentricity. And substituting all known values there, instead of you writing M times YT over IX, change M into P times E because this is due to the moment caused by eccentricity. Okay, so same is true as with the bottom part. So what about for the stress diagram for direct axial pressure due to force P? So what is the axial pressure? That is simply P over A. So with that, guys, the top and the bottom parts will both become P all over A. So, okay, so now, which of these values will we choose? Actually, we will be making use of all of them, then we will be adding them. And that is now our stress. So let me just compress them to one side in order for me to have a space on the right. So take note, guys, in our situation here at the top. So the tension at this particular side is actually no, sorry, not tension, but the stress at that side is compression. As you can see, since it is spoiler, since it is plotted to the left, then meaning it is negative. And for the next one here, since it is plotted to the right, or it is in tension, that is now positive. And for our direct axial compression, since it is compression, in my sign convention, that is now negative. And for the bottom part, for this one here, since it is tension, this is positive. For this one here, since it is compression, that is negative. And for this one here, since it is still compression, that is now negative. So with that, in order for me to solve for the total top tensile stress, I would be combining all of this. Then for the stresses at the bottom part, I will now be combining all of this. So proceeding, so for the total stress at the top, that is negative M times YT over IX plus PE times YT divided by IX minus P all over A. So, oops, sorry. This should be YB, and etc. Okay, so if we would now be collecting these ones at the bottom, so this is now our FB at the bottom part, okay? Or generally speaking, if you want to know the general equation, so this is now the general equation. So M times Y over IX, or positive negative MY over IX plus minus PEY over IX plus minus P all over A. Okay, so that is now our general formula. So, of course, this plus or minus would vary depending upon the force or the fibers that you are analyzing, if it is either top or bottom. Okay, so proceeding, as you can see, that we actually need the moment of inertias and the area. So from that, I would rather solve for them first before anything else. Or maybe I would first write the givens here. So it is according to the problem that the length is 15 meters. And it is to carry a superimposed dead load plus live load of 13.6 kilonewton per meter But take note, guys, it is said here that it is superimposed. When we say superimposed, it means that it is just on top it is now on top of the member itself. So meaning that the weight of the member itself is not included. So once again, let me write here superimposed. So if it is superimposed, meaning in Filipino, nakapatong lang siya. Hindi pa po kasama yung timbang ng beam mismo. Okay. Also, it is stated here that the eccentricity is 220 mm. So once again, that is now this distance here. This is 220 mm. So the initial pre-stressing force immediately after transfer is 800 kilonewtons. So this is now the P initial, that is 800 kilonewtons. So F prime C is equal to 35 megapascal, and initially the FC is equal to 27.6. Dependent pre-stress loss is equal to 15% according to the problem. And we will now be making use of Class U concrete or uncracked. Okay, so for the section properties, okay, so what are the values that we need once again? So of course, we must need to solve for first the area because we will be using it for P all over A. So for the area, so that is a matter of simple solid mensuration. So for the area, that is, well, for the area, I will now assuming it to be A. A is equal to, so as you can see here, we have, let's say this is area 1. And let's say that this is area 2. And this is, let's say, area 3. So for area 1, that is now the area of the flange. So if this is 500 and this is 125. So that is now 500 times 125. But take note, guys, that this area here is similar, or this is equivalent to this area here. So I would just simply multiply it by 2. Okay? So since I have already solved for the area at the flanges, so since I have already solved for the area here, which is 500 times 125 times 2, I will now get the area of the web. So for the area of the web, so its thickness is equal to 125 and times the height of the web. But take note that the height of the web is not 800. 800 is the total depth. So from that, what I would be doing is that I would be subtracting from the total depth, 800, the thickness of the flanges. So if this is also 125. So meaning that that is 800 minus 125 times 2. Okay, so this is now the area. And looking at the calculator to your left, that is 500 times 125 times 2 plus 125 times 800 minus 125 times 2. So my answer here is 193750 millimeters squared. So with that, guys, let me just store this to A. So I would be storing this to A so I could use it later on. So I have stored it to A. So and let me just move that here. So once again, I will be storing it to A, as you can see in our slide. So stored to A. Then next up, what else do we need? So you also need to solve for the moment of inertia, Ix. Okay, so for Ix, what is the moment of inertia of an I-beam? Well, actually, I do not know if there is a direct formula, but if you know, you could use it. But once again, I'm the one teaching here, so, well, I don't know. So I would rather make use of the basic principles of statics of rigid bodies. So it is either, since I know the moment of inertia of a rectangle, and as you can see that your I section here, are connected rectangles, I would rather make use of the formula 1 over 12 BH cubed. So this is now Ix. But take note, guys, if you would now be, let's say, getting or cutting this section here, so let's say that I will be cutting this section here and cutting another section here at the bottom. And let's say this is, let's say, figure 1, this is figure 2, and this is figure 3. if you would be getting the moment of inertia of 1, so that is 1 over 12 times b, which is 500, times h cubed, which is 125. And same is true as with the one below. Take note that if you would be making use of this formula, what you did was that you have solved for the moment of inertia about this point. Apologies for not, or for drawing not a straight line. And if that is now the center of your moment of inertia, what you should do is you should transfer it here. Okay? Since its centroid, or the centroid of that rectangle, did not coincide to the centroid of your figure. So thus, you must transfer it using the transfer formula, or plus AD squared. But since I am that person who is actually lazy to do that, I think you are too. So if that is the case, if I am correct, I would rather choose another method. And from that, what I would do is that I would get the moment of inertia of the whole section, assuming that there are no holes here, or there are no deductions there. I would assume that that is one whole rectangle. So let me just fix my figure. And from that, if that is one whole rectangle, guys, so meaning that its centroid is coincidentally located at the centroid of the section, because it is a rectangle. So from that, guys, I would not need to use a transfer formula since it has already coincided with the neutral axis of the whole section. So from that, that is now equal to 1 over 12 times b. My b is 500 times h, and h is 800. Then cube it. Okay. But the thing is, this is the moment of inertia of the rectangle. And since in our figure, it is not really a rectangle, rather it is an I section, what I would be doing next is that I would now, so for a moment, I would now remove these sections here. Okay? So I would remove these sections here. So from that, I would be subtracting from my equation 1 over 12 bh cubed of them. But let me solve for the b and the h first. So if this is, let's say, the b, if this is now its dimension b, that is now 500 minus 125 divided by 2. Okay? So that is 500 minus 125 divided by 2. So that is 187.5. So this is 187.5, as well as for the other one. And as for this height here, that is now equal to the total depth, which is 800. So the total depth is 800 minus twice of, so we have 2 thickness of flanges. So 2 times 125. So 125. So with that, guys, this is now 550. So from that, guys, proceeding, so we would now be subtracting minus 1 over 12 times b of 187.5 times 550 cubed. But take note that this is just the moment of inertia of 1, and coincidentally, both of them are equal. We would just be multiplying them by 2. So next question, do I still need a transfer formula here? We do not need to transfer any longer because their centroids also coincided with the centroid of this section. Okay? And if you want to make use of transfer formula, it would be up to you, but still, the value for d in AD squared would be 0. So it would just simply cancel out. So with that, Ix is now equal to, so let me just solve for it first using my calculator. So that is 500 times 800, 500 cube divided by 12 minus 1 over 12 times 187.5 times 550 cube times 2. Okay. So our answer is 1.6 613,411,458 times 10 raised to 10. And since that is very lengthy, napakahaba po, I would rather store this to B. So I would now be pressing Shift, Store B. Okay. So once that it has already stored to B, so let me just move this first to this location. So I have moved it here. Then proceeding. So what do we do now? So since I already know what the value of the moment of inertia Ix is and the area here, so again for our equation, we have MC over I and PEI over I and P all over A. So I think I already know everything except the value of M. Okay, so again, for letter A, we would now be solving for the stresses at the supports during the initial stage. So let me remind you guys that we have three stages of loading, I should say. And during the initial stage, only the concrete member has already been stressed, but it is still not subject to serviceability. So, meaning, if you would be going back here, and let's say that I will be displaying the givens here later on. So, again, during the initial stage, we will not be applying them with the superimposed loads. So, does that mean, guys, that we do not have loads at the initial stage? Actually, we still do, because even if we do not, we would not apply the superimposed load onto the member itself, it is still carrying its own weight, if you can still remember. So, since its own weight would now be for all stages, initial stage, final stage, it would carry its own weight. So, from that, guys, for our uniformly distributed load, and I will be subscripting this into SW, or its self weight, that is actually equal to the unit weight of concrete times the cross-sectional area of the concrete. So with that, guys, the unit weight of concrete is either you would be using 24 or 23.6. So maybe for the meantime, I would be making use of, let's say, 24. Again, it would be up to you if you want to make use of 23.6 or 24. But in my case here, I have used 24 kilonewtons per cubic meter. Or rather, I would rather make use of 23.6 for more accuracy. So, 23.6, apologies. So, kilonewtons per cubic meter times the area. What is the area? That is actually stored in A in my calculator. But take note that for that value, where was that again? For my value for A, this is in terms of millimeters squared. So if it is in terms of millimeters squared, where was my slide? So if this is in terms of millimeters squared, I would first convert this into meters first, or meters squared. So from that, guys, I would multiply this by a conversion factor of, for every 1 meter, I have, this is correct. So for every 1 meter, I have 1,000 meters. But take note, we must square it first. Okay? So in order for this to cancel out. Okay, so from that, guys, it will now leave you at an answer of 23.6 times the area, and that is written in my alpha A, or that is stored in my calculator as A, times 1 all over 1,000. But this must be squared. So from that, this is now 4.573 kilonewton per meter. Okay? So, since meter here would now be, meter cube will now be cancelled out by meter squared. So, it will leave us a value of kilonewton per meter. Okay. So, proceeding once again, that the self weight is equal to 5725 kilonewtons per meter. What is now the value for my M? So if you can remember that for the moment diagram, so if I am to draw the moment diagram here, apologies once again, let me just redraw my rather ugly beam. So let's say that this is now the beam and we have here the loads. If we are to solve for its moment diagram, so this is now what the moment diagram looks like. Take note that in our situation, it is a simply supported beam. So if this is now our moment diagram, the value here or the maximum moment is equal to WL squared all over 8. Okay? But take note that in our situation here, we are solving for the stresses at the supports. So meaning, we are now, for the moment, our concern is at the support and not really at the moment. From that, guys, as you know that for simply supported beams, there is zero or there are zero moments, I should say, zero po yung moments niya at the supports. So meaning that the moment here is equal to zero, thus we will now cancel this side of the equation. Okay? So let me just erase this first. So meaning that in our formula of, let's say, FB top, so for FB top, that is now equal to 0 plus P times E times YT divided by IX minus, so Y minus because P over A is compression, so that is minus P all over A. So from that, guys, for FB top, this is equal to 0 plus P. What is P, guys? So initially, at initial stage, the pre-stressing force there is 800 according to the given. So from that, this is now 800. But take note that this is in kilonewtons, okay? If this is in kilonewtons, it would be better if you would be converting it first into newtons for us to have a unit consistency. So from that, guys, I would be multiplying this by 1000 or times 10 raised to 3. Once again, this is in newtons. Then for E, what is the eccentricity? The eccentricity, according to the problem, is, what was that again? So, according to the problem, anong eccentricity natin? I forgot. The eccentricity is 220 mm. So, where am I? Okay, so this is 220 times 220. This is the, what do you call this? So, this is now the eccentricity. And what about for YT? YT is the distance, once again, from the neutral axis up until the topmost fiber. And if the whole depth is 800, meaning that this is 400 because it is symmetrical. So times 400 divided by IX. And if you can remember, I have stored it in B. So from that, this is now minus P all over A. So minus, what is P? Once again, that is 800,000 newtons divided by the area, and the area was stored in alpha A. So from that, for FB top, initially that is now equal to, so this is 800 times 1000 or times 10 raised to 3 times 220 times 400 divided by alpha B. So minus 800,000 divided by A. So this is now due to actual compressive force. So from that, the top or the stress at the top is 0.234. This is in terms of Newton per millimeter squared or mega Pascal. Okay, so this is now FB top. So let me just erase everything and let me write the answer at the top in order for us to have space. So for a moment, so let me just erase everything. So again, for FB top, this is equal to 0.234 megapascal. So what about for FB bot? So again, for FB bot, this will also cancel out since the moment there is equal to 0. And for the pre-stressing action for FB bot, I should say. So for FB bottom, this is now equal to 0 minus, since this one here is under compression, so minus P times E, or what is P once again? So P is now equal to 800,000. So 800 times 10 raised to 3 times E of 220 times YT of 400. Okay, so YC I should say. So YC is, of course, 400 divided by the moment of inertia B. Then minus P all over A, so that is 800 times 10 raised to 3 all over A. So coincidentally, in my calculator, what changes is just the sign. Okay? So it is just a coincidence because in our section it is a symmetric section. Thus, both YT and YB are coincidentally equal since our section is symmetrical. Okay, so from that, I would just change this here into a negative value. And let me just double check my equation. So times 220 times 400 divided by B minus 800,000 divided by A. So from that, the bottom part will now have a stress of negative 8.492 megapascal. And this negative sign here indicates that it is now under compression. Okay? So that is now for the initial stage. Okay, so now let us solve for the stresses at the midspan during the final stage. So what changes between the initial stage and the final stage? So for one, since we are already at the final stage, we are now to analyze this beam in such that it is actually already carrying its intended load or the superimposed load. So, meaning that the uniformly distributed load here is now equal to the uniformly distributed load of the self-weight or of its weight plus the uniformly distributed load of the superimposed load, which happens to be 13.6. So once again, that is already the combination of the dead load and the live load. So with that, guys, this is now equal to, so for the self-weight, actually I forgot what the answer is since I have erased it earlier, but it is equal to 23.6 times the area. So that is now unit weight times the area, and I would just be dividing this by 1000 squared. Okay, so if you're wondering where this come from, maybe rewind a little bit up until you reach where this formula was used. So with that, this is actually equal to 4.572. So 4.572 kilonewton per meter plus our superimposed load of 13.6. So adding both of them, so plus 13.6, that is now equal to 18.1725. Okay, so this is now equal to 18.1725. Okay, so now, since we are to analyze the midspan, the moment is not 0 any longer. So from that, guys, the moment that we will be using here, moment is now equal to, WL squared over 8. So once again, this is for simply supported beams. Okay, so substituting known value, this is now equal to 18.1725 times what is the length. So according to the problem, the length is 15 meters. So times 15 squared divided by 8. So from that, the moment is now equal to, so just multiply this by 15 squared divided by 8. So our moment is 511.102. But as you can see here, This is in terms of kilonewtons per meter. And this one here is in terms of meters. So meaning um, this is now kilonewtons or kilonewton meter. So from that, guys, the moment is 511.102, but I will be storing this to, let's say, M. So from that, guys, store to M. Okay? Just for the simplification of my solution. Okay, so proceeding, what else changes? Okay, so since we are already in the final stage, if I am to go back to our problem, it is said here that the value for P is equal to 800 kilonewtons. But take note, this P this P of 800 kilonewtons is only true if it is immediately after transfer. So this is just the initial. And it was also stated in the problem that it has a time-dependent pre-stress loss of 15%. So if you would be going back to our stages, so during the initial stage, our PI is equal to 800 kilonewtons. But during the intermediate stage up until the final stage, before it reached the final stage, it has lost 15%. Okay. So from that, guys, in order for us to know what the value of our new pre-stressing uh, force is, so our P final is now equal to 800 kilonewtons times 1 minus 0.15. Because if we would be removing 15% from 100%, that is now 85%. Or basically, if you would now be solving for this equation, this is 0.85. Okay? So 1 minus 0.15. So from that, the new pre-stressing force due to time-dependent pre-stress loss is 800 times 1 minus 0.15, and that would now give us an answer of 680 kilonewtons. Okay, so before I proceed, let me just remind you that we have only reduced 800 we have only reduced 15% from 800 kilonewtons in the final stage because it is a time-dependent pre-stress loss. But if, for example, that it is given in the problem that there was, let's say, a 15% instantaneous loss. So when we say instantaneous, has lost it, or it lost it at an instant amount of time, or sorry, that's actually incorrect. Instantly, I should say, meaning if you have an instantaneous loss, you should reduce the pre-stressing force also at the initial stage. So in Filipino, in Tagalog, kapag meron po kayong instantaneous loss, sa initial stage pa lang magbawas ka na. Kasi nga when you say instantaneous, at an instant, pagka pre-stress mo nawala agad siya. But then again, in our problem, it is time dependent. So it took time actually for it to be lost. Anyway, so going back to our figure here. So that is 680 kilonewtons. So what is now our equation here? So this is negative, this is positive, and this is negative. So from that, our FB top is equal to, so moment times YT. So our moment was actually stored in M in my calculator times, what is YT still? That is 400 mm. But take note, before I proceed or before I multiply it by 400 mm, if you can remember for the value of M, so let me just recall M. So alpha M, that is equal to, oops, was this the moment? So apologies. Did I really? So let me just resolve 18.175 times 15 squared divided by 8. So that is 511, and let me store that to M. Okay. So once again, since we're already here, take note that the value of M is in terms of kilonewton meters. Okay? And in order for us to in order for us to have a consistent unit analysis, it would be better if we would be converting it first to um, Newton millimeter. Okay, so from that, if you are to convert kilonewton meter into Newton millimeter, you must be multiplying it by 1 million or times 10 raised to 6. So once again, this is just a conversion factor. Times YT of 400 mm divided by the moment of inertia, which was stored in alpha B in my calculator. So once again, this should be negative since it is compression. So plus P. So our new P once again is 680. So from that po, so plus 680, but this is in kilonewton. So multiply it by our conversion factor first. Times E. E is 220. It did not change since it is constant eccentricity. Times YT once again of 400. So this would be divided by Ix of also B minus P, that is 680 times 10 raised to 3 divided by area. So from that, FB top is now equal to, so let me confirm the value of M once again. So that is, that was 511.10125. So, okay. So that is alpha M times 10 raised to 6 times 400. Oops, sorry. Times 400 divided by alpha B. But take note that this should be negative. Plus 680 times 1,000 or times 10 raised to 3 times 220 times 400 divided by alpha B minus 680 times 1,000 divided by alpha A. Okay? So from that, the stress at the top is now equal to negative 12.472. This is now in terms of megapascal. Okay, so next up, what about for FB at the bottom? So for FB bottom, so for, once again, for FB bottom, so this is negative, this is positive, this is negative, and this is negative. Unlike a while ago, so a while ago, that is positive, negative, positive, and then negative. And this time, that is now positive, negative, negative. Okay, so from that, M, positive M times 400 divided by B. Oops, sorry. I forgot the conversion factors. So that is M times 10 raised to 6 times 400 divided by B minus 680 times 10 raised to 3 times 400 divided by B minus P all over A, so that is 680 times 10 raised to 3 divided by A. So coincidentally, I would just change the signs in my calculator. So this would now become positive. So M times 10 raised to 6 times 400 divided by B plus, so this should now be negative. So minus 680 times 10 raised to 3 or times 1,000 times, oops, sorry, I forgot the eccentricity here. So times 220. So times 220 times 400 divided by alpha B minus 680 times 10 raised to 3 or times 1,000 divided by A. So our answer here is now 5.453 3 megapascal. So since this is positive, this is now under tension. Then from a while ago, since this is negative, this is now under compression. Okay. So next problem, or the next thing that we will now do, is for us to check for the allowable stresses. So again, we will be solving for the allowable stress for initial and also for final. So for the initial part, if you can remember, during the initial part, we have solved for the adequacy. We have solved for the stresses at the supports. Okay? So at the supports, so going back here, so during the initial stage, so meaning that we will now be making use of B here because this is now for extreme fiber stress in compression at the ends. Okay? So at the ends. So that is now for support. And if we were now to choose from these columns here, it was stated in the problem that we will now be analyzing the uncracked. Okay? So meaning, we will be making use of 0.7 FCI prime. And from that is now equal to 0.7 times what? So that is now the compressive force initially. And according to the problem, initially, the FC prime I is 27.6. So just multiply it by 27.6. So from that is now equal to, so 27.6 times 0.7. So the allowable is 19.32 megapascal. Okay, so what about for the tension? Because if you can remember from earlier, not here, but from earlier that aside from compression, we also have a tension part in the initial stage. So going back to our table here, so we also need to get the value of FTI. So it is either this one or this one. So if we are to read it, so this here is the extreme fiber stress in tension immediately after transfer. And for this one here, this is the extreme fiber stress in tension at ends of simply supported members. So if it is at ends, meaning that we will now be making use of this one here. And substituting known values. So this is now equal to. So this is equal to. So let me just substitute it already. So that is 0.5 times the square root of FCI prime. So initially, so that is once again 27.6. So from that, the answer here is 2.627. So 2.627. So once again, both of them are from the initial stage. Then for the final stage, so let me just change the ink color. So for the final stage, it will now be dependent upon these three values. So you would now be making use of this one here if you are solving for the extreme fiber stress in compression due to pre-stress plus sustained loads. And you would now be making use of this one here if you would now be making use, or if you would now be analyzing extreme fiber stress in compression due to pre-stress plus total load. Okay, so which one of this will we use? So if we will be going back to our previous slide, it is stated here that it is to carry a superimposed dead load plus live load. Okay, so what is the difference, guys, between sustained loads and total loads? So if you would be Googling the term sustained loads, these are now loads that would act throughout. So loads throughout the life of the beam. So the lifespan of beam. Okay. So rather, these are permanent loads. So meaning if you're analyzing for dead loads only, so meaning, guys, that you will now be making use of this value. So when we say total load, these are now the sustained loads plus transient loads. So meaning that for total loads, this is now the combination of permanent loads and rather some transient loads or temporary loads. So since it is not given in the problem, we could assume that we would now be considering total load because, once again, from the problem, we are now to consider the self-weight, the superimposed dead load, plus the live load, which is actually considered generally as a transient load. Okay? So, again, since it is not indicated in the problem, let us now assess it as a total load. Okay? So, from that, let me just erase these definitions here. So, from that, guys, for our total, for our final compressive force, this is now the limit, which is 0.6 F prime C. And multiplying it, that is now equal to 0.6 times F prime C. But the F prime C, this is now the compressive stress at the final condition or at the final stage. And the final stage is 35 megapascal since it has already cured. So from that, this is now equal to, so 0.6 times 35. So that is now 21 megapascals. Then for the tension side, that is now 0.62 times square root of F prime C. So from that, that is a 0.62 times square root of 35. So the answer here is 3.67. So these are now the allowable loads according to NSCP. Okay? Okay, so these are now our answers po for the allowable stresses according to NSCP. So at the initial stage, that is 19.32 for compression. Then for tension, that is 2.627. At the final stage for compression, that is 21. And for tension, that is 3.67. So the next question in the problem is for us to check the adequacy of the beam. So what we would be doing there is that we would just be comparing our answers from earlier if it is still within the limit. So going to my summary, as you can see here, the one on the right are your actual and the one on the left are your what do you call this? The one on the left are the allowable. So this was the allowable. And this one here is for the actual. So since the allowable is greater than the actual, for the initial stage for compression, this actually have passed, so meaning that it is adequate. And since the allowable here is greater than the actual, it is still adequate. So for the final stage, since the allowable is also greater than the actual of 12.472, that is still adequate. But for the last one, since the allowable is 3.67 and the actual is 5.453, so the actual is actually greater than the allowable, so meaning that this is not adequate. So collectively speaking, since one of the criterias or one of the criteria was not satisfied, meaning section is not adequate. Okay, so that is now our final answer for this problem.